Hobart School of Welding Technology presents Training in Oxy-Acetylene Welding, Cutting, and Brazing. Topic number 25, Lecture Discussion. Introduction to Brazing and Braze Welding. The objective of this topic is to be able to identify the principles of brazing and braze welding. Both brazing and braze welding are processes which involve temperatures above 800 degrees Fahrenheit, but below the melting point of the base metal. Non-ferrous filler metal is used to form the union. Brazing is the term used when the filler metal is distributed in a thin film between two or more tightly fitted pieces of base metal. The film thickness is usually between 1 and 3/1000ths of an inch thick, about the same as 2 sheets of writing paper. The process is sometimes called silver brazing or silver soldering. The brazing of a joint this thin depends on capillary attraction, the tendency for liquids to spread out between closely spaced materials. We can demonstrate this with 2 pieces of glass spaced about 1/1000th of an inch along one edge and about 10/1000ths inch along the opposite edge. If we dip the edges in colored ink, we see that the ink rises highly in a very thinly spaced area and only a smaller amount in the wider spaced area. When 2 pieces of cleaned and fluxed metal are placed tightly together and heated to the proper temperature, the filler metal will flow into the space just as the ink did, as seen here in slow motion. The most common types of joints used for brazing are lap and butt joints or combinations. The most common methods of heating to brazing temperatures are furnace, induction, flux bath, and torch. In furnace brazing, the parts are placed in a heated oven-like chamber with the filler metal and flux in place. The parts may be put in with conveyor belts or in batches on trays. Induction brazing uses heat from an electric current within the parts, which is caused to flow by a separate current flowing in coils around the part. Salt flux brazing uses a heated molten salt bath to bring the parts up to temperature. Of greatest interest to the welder is torch brazing. The process consists of cleaning the mating surfaces of the joints, coating them with flux, placing them tightly together, heating the joint area to the melting point of the filler metal, and adding the filler to the edge of the joint, allowing capillary attraction to draw the metal into the joint. Watching the behavior of the flux is the best way to determine when to add the filler metal. The flux first dries out as the moisture boils out. Then the flux turns a milky color and starts to bubble. And finally, it turns into a clear liquid at about 1100 degrees Fahrenheit. This clear appearance is the indication that the filler metal can be added. The heat of the joint, rather than the flame, should melt the filler metal. If the temperature and alignment are proper, the filler will spread over and into the joint. The filler should flow evenly, form a good bond, and melt at a temperature less than the melting temperature of the metals being joined. With proper preheating and fluxing, a workpiece can be brazed in any position. Filler metals are made up of various combinations of copper, copper zinc, magnesium, aluminum silicon, copper phosphorus, gold, silver, and nickel. The flux used to eliminate oxides and contaminants are made up mainly of borax, boric acid, chlorides, and fluorides. They are formulated to suit the metals being joined and come as powders, as paste, or as liquids. Fluxes are not needed in furnaces with controlled atmospheres of inert gases, such as nitrogen, ammonia, carbon dioxide or monoxide, and so on, since these take the place of the flux in preventing oxidation or contamination. Because of their composition, nearly all fluxes give off fumes that may be toxic, so they must always be used in well-ventilated spaces. Braze welding looks similar to fusion welding, except that non-ferrous filler metal is used and the base metal is not melted. Typical joint designs are the same as for fusion welding: the butt, lap, corner, and T-joint. Depending on the cleanliness of the base metals before braze welding, a procedure called tinning may need to be performed. To tin, the surfaces of the joint are cleaned by brushing or grinding. If they are ground, light filing and wire brushing is needed to remove any residue. Cleaning with a flame set for a highly oxidizing condition will burn off any remaining contaminants. Then flux is added to the joint or applied to the brazing rod during the tinning operation. Some rods are available with a flux coating already applied, similar to certain kinds of welding electrodes. The metal must be preheated to open the pores of the material. Then the surface of the joint is coated with a thin film of filler metal. This ensures a strong bond between braze weld and base metal. After tinning, the joint is then filled with as many passes as necessary. Unlike brazing, braze welding is not recommended for out-of-position work, since this process does not use capillary attraction and the highly fluid filler metal simply runs out of the joint. However, on small welds with close control, it is possible to braze weld in positions other than flat. Brazing and braze welding offer certain advantages over other joining processes, as they do not affect the heat treatment of the original material as much as welding, nor do they warp the original metal as much, and they offer the advantage of joining dissimilar metals. Some common braze welding faults are too large a root opening, resulting in excessive reinforcement, not enough heat, which causes a narrow, inconsistent braze weld with lack of penetration in spots, too much oxygen, which causes the weld to be depressed in the root area, too fast a travel speed, which produces a narrow braze weld similar to insufficient heat, and too much heat, which causes the face to be depressed into the root opening. The black edges are the result of burned zinc oxide. However, with care and practice, you should be well able to produce quality braze welds.